Hi everyone, today we are going to get into a very kind of cool and fun topic, which is the atomistic basis of linear elasticity and Young's modulus. So we've learned about all these different properties that we talked about in our elastic regime. So Young's modulus, the stress at failure, all of these are, stress at failure is a little different one. But anyways, Young's modulus specifically. And these aren't just values in the stress strain curve. So in the elastic regime, we can actually derive some fundamental expressions to kind of see how do we get these material properties, because we are, strictly speaking, we are just simply stretching the bonds. So if we remember back to our most important potential, our Leonard-Jones potential, it looks a little bit like this. So we are essentially taking these atoms that are at their equilibrium position, lowest energy, where they're just touching, and we're stretching them. If we're, in tension, if we're in compression, we're pushing them closer together. But anyways, or they're overlapping even more. But we're essentially changing the energy of our system, specifically the internal energy of our system. So we previously calculated what's the elastic strain energy, but we can actually relate things like stiffness, the Young's modulus, to this potential. And we can actually calculate that from these potentials. So let's go ahead and let's derive, and stiffness we'll see for other systems that it's going to be, for metals, our stiffness is really going to come from pulling and stretching these bonds. But we're going to see for other materials, rubbers, polymers, that the stiffness is going to be entirely an entropic effect. So we'll get to that in just a little bit. So let's go ahead and let's look at, and let's calculate essentially this from a thermodynamic perspective. So let's look at a system that's under uniaxial tension in the one direction, and we're going to calculate the internal energy of our system. So again, because we're increasing, and actually if you see here on the next page, we are going to go from state 1, which is our equilibrium position, to our state 2, which is where we're displacing our atoms. So if you see going from state 1 to state 2, energetically unfavorable because we're increasing the energy of our system from here to here. But let's actually kind of calculate what is this change, and most importantly, can we derive an expression that gives us our Young's modulus, or stiffness of the material. So we know from our thermodynamics, basically refresh, hopefully you all understand, you remember it too, to calculate the internal energy of our system by summing the work and then the heat. So work, we've already done several of these calculations before. If I have a system that is, simply, go over here. If I have a system that we're basically pulling in one direction, I could calculate the work. So I'm applying a stress. My stress is Newton per meter squared. So where's the stress being acted upon? Being acted on an area 2, basically this area here. So delta 2, delta 3. So that's my force. And then how is this force? How can I relate that to, again, I know that my work is force times some displacement, delta x in general. So how do I figure out my delta? Well, I know it's being strained in the 1 direction. Again, differentially, so small element. So I know my strain in the 1 is just going to be my change in the 1 direction divided by my delta 1. So I can rearrange this if I just want to see what's the displacement here, the delta 1. Again, this is like a little differential displacement. I could just bring this over here. So I've got this, and this expression reduces to stress times that strain, and then this, and this. Those are volume elements. So you can double check again, Newton per meter squared times volume meter cubed. That's going to give me Newton meter. That's an energy. So calculating the work is not too bad. And we've kind of done it before. Again, remember your elastic strain energy calculation. Look back at those notes as you go through it. But we also know, and we could calculate and figure out what is our expression for heat, dq. And again, that's just from your second law of thermodynamics. So if you rewrite this expression, this is our expression for the internal energy of our system. And you can rearrange this in terms of stress. So moving all these guys over, and you see we have these two terms here, where our stress is dependent on what's the change in the internal energy of our system with respect to strain. So again, as we strain our material, we're stretching the bonds, and they're going to displace our atoms, and that's going to change my energy. But you also see this term where there's a change in entropy as we strain our materials as well. Now this is where, here's the rub, essentially. We're going to focus first, and actually we'll kind of finish it in another video. This is kind of just a nice little introduction. But we are going to focus first on metals and many crystal materials, and specifically this full derivation that we're going to get into in just a second, where we're going to calculate essentially two ways, but this derivation is going to hold because we're making a very critical assumption. For most crystalline materials, metals, ceramics, so this holds for most metals, most ceramics, amorphous materials as well that are below the TG. So we need to be well below TG, i.e. we need to be a glassy polymer or a glassy amorphous material. So if that's the case, DSDE is going to be very small to the point where we are just going to, again, for this particular class of materials, we're going to neglect it entirely. Now, there are lots of different polymers, biomaterials, et cetera, other elastomers that are going to be well above TG. And in that case, we're going to see that not only is this important, but most of our elasticity comes from that change in entropy as we change our strength, essentially. So your Young's modulus is going to be primarily a function of this. So the next video, we're going to kind of do two derivations and then show we get pretty much the same answer. One's a little bit more accurate, or we can, it's a little bit of a loose term, but all right, we'll see you in the next video and we're going to analyze this.